So good afternoon, everyone. So we had actually seen this Wheatstone bridge. So today we have to see your AC bridge. Okay. So I will ask you first. How many of you solved this question? Did we solve this question or not? Someone said me B. So you are saying A. Nitish is saying A. Okay. This question we had solved. What about this one? Nitish is saying C. What about others? Rishir and Sunny. This one? 200 ohm. 200.
No, sir, I need to check. I think I found the value of R.
Pardon,
I'll
I
check.
couldn't hear you.
I
Wait a
need
second.
to.
Just wait a second. Now tell.
I need to actually cross-check this question. I solved
Uh,
it
Recheck
few
once
days ago.
again. This will not
Yes,
be
sir.
200 because 200 will cause a more voltage change. Okay, greater than zero point 0.1. So resolution, if it is so less, so means resolution is basically what? It is the minimum change. Okay, minimum change in input that is reflected in this meter. So for 200 ohm means all the resistance here are 100, so you can expect that this del r, it won't be means like 20% of this value. Okay, 20%. So that is very bad meter then. Okay, so it won't happen. What about others? We were enjoying means 1 week we didn't have class from Tuesday. Okay, so we were enjoying or what? See, this is not good. Okay, because if you don't solve questions, how will you get to know whether you have understood a problem or understood a concept or not? Okay, so that is not good. So today I will solve. From next time onwards, everyone please try. See, getting answers,
Yes,
it is irrelevant. Okay, it's irrelevant.
I tried solving, but I couldn't get the answer.
Okay, fine, no issues, no issues. Okay, so getting answer is irrelevant at this point of time. Okay, till the month of October, I will say just focus on getting what? Just focus that you are at least able to grasp the concept. Okay. Even time is irrelevant. Time taken for solving the question is irrelevant at this particular time. After October, I will stress that October, November, December, January, this 4 month, your main aim should be to optimize time to get the correct answer. Okay, so you should use the least amount of time to get the correct answer, but at this point I will say you just try. You try to focus on grasping the concepts. Okay, that's it. Chalo, so we will start this. What is given in the Wheatstone bridge shown in below figure? When resistance R1, so I had marked this as R1, increases by 1 ohm, so R1 increases by 1 ohm, the current through galvanometer is. Okay, so what is the current through galvanometer? Now what should we do? Because this R1 is increased through 1000 and means 1 ohm. So now this is 1001 ohm. So now here you can see all the values are in microampere. If this was in your ampere, so you could have said this will be approximately equal to 0. Okay, if this all the options were in ampere, you could have said very easily that this is going to be a very negligible amount of current. Okay, but the answer over here, it is given in microamps, so you cannot neglect this value of current. So what we need to do, usually we solve this question using Thevenin theorem. Okay, Thevenin's theorem. So what is asked? Basically you have to find the current through this galvanometer. See, I have written detector over here. So this detector is basically what? This is your galvanometer. So you have to detect the current. So what you are going to do, just give me a second. হ্যাঁ কাকা, আমি ক্লাসে আছি, আমি পরে কথা বলছি তোমার সাথে। ক্লাসে আছি, ক্লাসে পরে কথা বলছি। Huh. So current through this galvanometer. So what I am going to do, basically, I am going to Thévenize from this terminals, okay? From this two port, I am going to Thévenize my circuit, okay? So we know what Thevenin voltage is. What it is, your open circuit voltage. Okay, open circuited voltage. That means what? I have to open this two terminal, or this port needs to be open circuited. Okay, fine. So let us try to find then. So I am making changes in the same diagram, but you need to draw one more diagram if you are solving at this point of time. So you can see basically current through the galvanometer. So they have asked the magnitude. Okay, they have asked magnitude. They haven't told the direction. So it's okay. As you can see, resistance at this point, it is more. So the voltage drop will be also more. So let me mark this position as plus, this as minus. So this is A, this is B. So VTH is equal to VB. Okay. So now what is VTH? This is equal to VA minus VB. So VA is equal to what? It is equal to 10 into 1001 divided by, I am using voltage divider, because if suppose current I is flowing from here, so this will be I1, this will be I2. You can see this 1 kilo ohm and this 1001 ohm, they two are in series, and even these two are in series, so I can use voltage divider theorem. Okay, any doubt up to this point, anyone? Any doubt?
No, sir.
No need to write no, sir. You can just write NY. Okay, that's it. N for no, Y for yes. Okay. So where was I? Voltage divider. So this will be equal to 2001, 1 kilo ohm plus 1001 minus 10 into, this is simple, 1000 divided by 2000. So tell me what value do you get for this one? I don't have calculator. You guys need to have calculator with you at all times. What answer? Now even I have to sit with calculator. What does this mean? Tell me in, okay, 0 point means 3 millivolt. Exactly 3 millivolt. Or have you done some approximation? Tell me the correct answer.
So
मेरे से ही solve
2.49
कर रहा
into
हूँ.
10 to the power minus 3.
Pardon? Once again tell me what?
So 2.49 into 10 to the power minus 3.
Okay, fine. So even you can add one more number over here after decimal. Okay. So 2.49 what? What is the next digit after this? Because you can see this is in micro, or else it's okay. This much can work.
2.498.
It's okay. It's okay. Because everything is in two decimal after two decimal places. So this is okay. So this is in ampere. So this is what? This is your VTH. Now next, what do we have to find? We have to find RTH. Okay. Now RTH, you know, basically RTH is equal to VDC by IDC when all independent sources are equal to 0. Okay. This is the case when we have dependent source. If we don't have dependent source, then what we do? For calculating the Thevenin resistance from the terminal, we basically do what? Voltage source needs to be short circuited and current source needs to be open circuited. So here you can see there is only this one voltage source. So I have to short it. So if I short this one, what you can see? Which two are in series and which two are in parallel? So you can very easily see from here that basically this two means, sorry, okay, if it is difficult for you, so what you can do, basically look very carefully. Okay, if you do this and simply I have explained this to Nitish already that how we actually do all this thing. But others like Sunny and Shishi, you might have studied from Prashant sir. So I don't know if he has told you this or not. So there are various way to do actually. Okay, various way to calculate your equivalent resistance. But the simplest one for this particular question, you can see that this 1 kilo ohm, 1 kilo ohm, it is in what? It is in your parallel, because this whole circuit, I can make it like this. This short circuit, I am replacing it with a point. Okay. Once again, so this is 1 kilo ohm means 1000, and this is 2000, sorry, 1001, and this is 1 kilo ohm, 1 kilo ohm. So this combination will be 500 ohm plus this will be what? 1000 into 1001 divided by 2001. Tell me what value you get in ohm for this one.
So 500.749.
500.749. So this is the value of RTH. So this is your RTH. So now let me draw the equivalent circuit. So the equivalent circuit will be something like this. Now don't forget your galvanometer. Yes, tell me, Nitish, what happened?
The RTH value should be plus 500 also, like 1000 point.
Oh
Yes,
yes, yes, yes. So this will be
plus
1000 point.
500
Yeah, yeah.
to
Yeah, yeah.
1000.
Sorry, 1000.749. Yeah. Okay, so this answer is in 2.49 milliampere. Okay, this is what? This is your RTH. RTH comes out to be 1.749 kilo ohm, and galvanometer had resistance what? Okay, so I have erased it. I guess it was 1 kilo. Okay, means I have erased it. So now I cannot find. Okay, so it's okay. So now I have to find this current. So current is equal to what? Already you have this in milliampere divided by, if you directly do this in kilo, you will get in microampere. So that is 2.749. So tell me what is the answer in microamp. Is it A, B, C, D? What it is? 2.49 divided by 2.74. Array, none of the options are going to match. Why? None of the option will match.
Sir, I think
Where
the RTH is 1000.25. It's coming.
1000 point? अरे यार, you guys कैसे होगा मतलब? What are you guys doing now? I am very much scared with you guys. Okay, so I have to check. 10 into what it is? 1001 divided by 2001 minus 0.5. No, this was correct. 2.49.
Sir, RTH.
So RTH it is 1000.249.
Yeah.
Who said 749?
Yes,
Did
I
I?
said it.
It's okay. So this will be what then? 2 point. So this is approximately coming out to be 2.249. Okay. So I guess A will be your answer if I am not wrong. 2.49 divided by 2.249. 1.10. Yeah. So approximately option A. So this is 1. 0.10 microamps, so approximately equal to 1.25 microampere. Okay, any doubt? So see, these all questions are just for your calculation, that if you are able to calculate things or not. There was no concept anywhere. Okay, no concept. Any doubt in this question, Sunny, Nitish, Shishir? चलो आगे बढ़ते हैं फिर. Okay, so this question, option C. What is the question? The resistance value of the bridge circuit shown in the figure are R1 is equal to R2 is equal to R3 is equal to R. Okay, so all these values are R. Fine. And R4 is equal to R plus del R. The bridge is balanced by introducing a small voltage V. So what is said? That this bridge is balanced. The value of del R is. Now, one thing to note over here is that the bridge is balanced. How can it be balanced? See, if you do basically the product of opposite arms, so this is R into R is equal to R into R plus del R. Okay, so you can see basically that the resistance, this is not equal. So how are they telling that the bridge is balanced? It has been balanced due to, means you can see, means sorry, it is unbalanced due to this del R. Now this del R, basically what it will do, it will create a potential difference between these 2 points. Previously in this question, you can see that there was no current flowing. Why? Because the potential difference between these 2 points was same. Okay, it was same. That is why no current was flowing through galvanometer. But what is happening here, you can see due to this del R, there is some potential difference created, and to actually nullify that potential difference, we have added one small voltage in this arm so that the bridge is balanced. That is why we are able to say that this configuration, in this configuration, your bridge is balanced. So we have to basically find what? We have to find this value of del R. So how can we do? If this bridge is balanced, what we can say, let me assume this current is I. If this is I1, this is I2. So if this bridge is balanced, okay, if this bridge is balanced, so what all things can we say at this particular time? That potential difference at this point is same as potential difference at this point. So basically what I can do, you can see, or it is okay, wait a minute, yeah, it's fine, so we can do anything. Simply what you have to do, apply KVL in this loop, in this direction. In this direction, I'm going to apply KVL. So if I apply, so it will be what? R into I1, and this is, you can see I am going opposite to the direction of current. So this will be R plus del R into I2. So what we get? RI1 is equal to R plus del R okay. So this is the value we are getting. Now same thing, once again apply KVL in this loop. So if we apply KVL in this loop, okay, so we need the value of what? Del R, na? Okay, so I2 will be required, I think, yes. Okay, fine. So once again apply KVL in this loop, in this direction. Okay. So if I apply, if I start from here, so this will be R I1, and in this direction, so opposite, so minus V minus RI2 is equal to 0. So this comes out to be Ri1 is equal to V plus Ri2. Okay, this we get. So now I can substitute this in the above equation. If I substitute it, what will I get? V plus Ri2 is equal to is equal to Ri2 plus del Ri2. So R, okay, so this is I2. Ri2 gets cancelled. So del R is equal to V by I2. Now I need to find this I2. I need to find. If I am able to find this I2, then my question is complete. So how can you find I2? Can you tell me how to find I2? So for finding out I2, it is very simple. Just apply one more KVL. KVL in which loop? I will start from here, from this point. Okay. So let us do that. Minus E plus, this is once again R plus, means this will be 2R plus del R minus, sorry, I2 and plus V is equal to 0. So I2 is equal to what? E minus V divided by 2R plus del R. So simply substitute I2 is equal to V by del R. So instead of this, I am substituting V by del R. Let us cross multiply. So this is 2RV plus V del R, and this is equal to del R E. Question is getting complex. Del R E minus V del R. So now let us see what all things can be subtracted from here. Just wait a minute. 2RV, 2, sorry, V del R, and this is okay, fine. So let us take this term over here. So this is 2RV is equal to, these two are same. So this will be del R common E minus 2V. So del R is equal to E minus 2V by 2RV. Any option? So I am getting something else. Why am I getting the opposite thing?
Sir, it's correct only. You just wrote it wrong. It's correct.
Oh yes, I wrote it wrong. So that is okay. Not good. Okay. Yes, sorry. So this is 2RV minus E minus 2V. Okay. So this is the answer. So you have to apply 3 loops over here. So one thing I can see that we didn't require this one. This was not required. This loop was not required. Okay. Directly we could have done it from here also. No, actually R1 we had to substitute it once again. No, it was required. So maybe I am writing in haphazard manner. That is why it is looking like this. But you can see it's very simple. It's just substitution. Okay, substitution. So any doubt, let me know. Any doubt? Fine. So then this question. So what is the question? The unbalanced voltage of the Wheatstone bridge shown in the figure is measured using a digital voltmeter having infinite input impedance. So what does this much mean? What does this sentence mean to you? Having infinite input impedance, what is it measuring? Don't say, sir, it's measuring voltage. I also know it's already given, it's voltmeter. So don't say it that voltage is being measured. What kind of voltage is being measured? Having infinite input impedance. What do we mean by this? That this voltmeter has what? Open circuit voltage. Very good. That means Thevenin voltage it is measuring. So that is why we always connect voltmeter in parallel. Why? Because voltmeter have infinite resistance. So if I want to measure the voltage across this 2 ohm, I will connect it in parallel with 2 ohm. If suppose I connect it in series, if suppose I connected this voltmeter somewhere over here. Now this has infinite resistance, so no current will flow, approximately 0 ampere, so I cannot measure any voltage drop. Okay, so that is why voltmeter is connected in parallel and ammeter in series, because ammeter has approximately equal to 0 resistance and voltmeter has approximately infinite resistance. Okay, so ammeter measures your Norton current or short circuit current. Voltmeter measures your Thevenin voltage or open circuited voltage. So these things need to be known by you. Okay, chalo. Now what is said, shown in the figure is measured using a digital voltmeter having infinite input impedance and resolution of 0.1 millivolt. Resolution means what? That this voltmeter it can measure in the what we have to say, means it can measure in the not multiples, actually means it can measure like 0. Next measurement will be 0.1 millivolt. Next can be zero point 0.2 millivolt, like this. Okay. It cannot measure 0.01 millivolt or 1.11 millivolt. No, you cannot measure like this. Either you can measure 1.2 millivolt, 1.3 millivolt, like this. Means after one decimal place only you can measure. So resolution is basically what? Resolution is the minimum change that your voltmeter or an instrument can detect without any error. Okay. Is it clear? Is it clear? What is resolution?
Yes, sir.
See, resolution, one more thing. See, like you, if you go to this goldsmith and if you take this weight scale of the vegetable sellers, you cannot buy gold. Okay, why? Because they have weights in the range of 250 gram, 500 gram, 1 kg, 2 kg. You never purchase gold in those ratio, means in those proportions. Okay, so for gold you require a weighing scale which has very less resolution compared to a weight scale that is used in vegetable shop. Okay, so that is basically resolution. So resolution of this is 0.1 millivolt. If R is equal to 1000 ohm, the minimum value of del R in ohm to create a detectable unbalanced voltage. So they are basically asking for what value of del R, for what value of del R you will get zero point 0.1 millivolt over here. So initially your bridge is balanced. Okay, initially your bridge is balanced when this del R was not present. You can see if you multiply the resistance in the opposite branches, it is equal. Okay, so what happens, you have to, we are introducing as the smallest possible resistance over here. We are introducing the smallest possible resistance over here so that our voltmeter is having 0.1 millivolt. We have to do that. So now how can we do that? So we have to get 0.1 millivolt. Fine. So what can we do? Tell me, what can we do?
So we can like take the potential difference across time.
Yes, very good. Once again, if we take the Thevenite, if we Thevenize, or simply not even Thevenize, we know what that 0 ampere current is flowing through here. Means if I assume I is flowing from here and I1 is flowing in this branch and I2 in this branch, so you can see I2 is flowing through this R as well as this R. I1 is flowing through this R as well as this R. That means we can simply apply voltage divider theorem. How? Let me assume this is plus side, this is minus side, this is A, this is B terminal. So VA minus VB is equal to 0.1 millivolt. Okay. So what is VA? VA is equal to R plus del R, means R plus del R by this will be 2R plus del R minus this will be 1 by 2. Okay, I will not write it directly. R plus R. This is for this branch. Voltage divider theorem, simple. Into 2 is equal to 0.1 millivolt. Now, see very carefully. Here your answer is asked in ohm. So it is better to convert or kilo ohm to ohm and millivolt to volt. Okay. So let us write this as this is 0.1 millivolt. So this will be minus 10 to the power 4 volt. So now let us put the value of R over here. So R is 1000 ohm. So 1000 plus del R. This will be 2000 plus del R minus 0.5 half into 2 is equal to 10 to the power minus 4. So I need to find this del R. So what we can do over here is 2 into 1000 plus del R divided by 2000 plus del R minus 1. So this minus 1 will come over this side. So this will be 1.001. And if I bring this 2 over this side, or else it's okay, 2000 plus 2 del R is equal to, this will be what? 1.0001 into 2000 plus 1.0001 del R. So approximately what you can do, no, we can't approximate over here because this is asked in ohm. Okay, so we cannot approximate. This will be a very small value. So let us solve this. Tell me what value are you getting for del R over here. So this will be 2 del R minus 1.0001 del R is equal to 2000, sorry, yeah, 2000 common, means this will be into 2.0001. Tell me what value you are getting. I am unable to solve now. Del R is equal to what? 0.2. Okay, so this is 0.2. So 200 was not the correct answer. 0.2 ohm is the correct answer. Tell me, any doubt? Nitish, Shishir, Sunny, any doubt? Okay, fine. So now we have the concept of AC bridge. Okay, so how many of you are from instrumentation? Nitish, I think. So this is known as actually quarter bridge. Okay, quarter bridge arrangement. When we study strain gauge, at that time you will see that we will get once again such kind of bridges. Okay, so this is quarter bridge arrangement. Fine. Next we have is what now? AC bridges. Now, why do we need to study AC bridges? Why can't we just stay with your DC bridges? Can anyone tell me? Why do we need AC bridge? Already I have told you, with the help of DC bridge, I can measure only resistance. I cannot measure inductor as well as means inductance or capacitance. I cannot measure using DC bridges. For that, I always require AC bridge. Okay. So in AC bridges, we have your frequency also, frequency component. So let us assume we have impedances Z1, Z2, Z3, Z4. Okay. So this impedance, basically it is represented in your complex form. So Z1, let me write it in polar form, in, or you can even say in your magnitude phase form. Polar form means what? If suppose I have this form. So this is known as rectangular form, rect form. So if I want to write in magnitude phase form, so this will be what? You have to take magnitude of this. Phase will be what? Tan inverse of y by x, so that will be 1. So this is root 2. Phase will be pi by 4. If you want to write in radian or if you want to write in degree, it's up to you, whichever way you wish to write. So this is your polar form. Okay, polar form. If you want to write it in exponential form, complex exponential form, so you can write it like root 2 e to the power j pi by 4. Okay, you can write it like this. So this is what? Complex exponential form. Why? Because we know e to the power j phi. What we can write? What is this theorem called? What is this theorem? Yes, very good. Okay. Euler's theorem. Chalo, good. Acha. So now I want to write this Z1 in your polar form. So let the magnitude be Z1, phase be phi 1, Z2 is equal to Z2, phi 2, Z3 is equal to mod Z3, angle is phi 3, and Z4 is equal to Z4, magnitude of Z4, angle of phi 4. Okay. So these are the magnitude of all this impedances. Okay. Fine. Now this is one AC bridge. So let me see what we can do. Okay, fine. See, as this is AC bridge, I am not going to mark any polarities. This is E4, you can see. So now for the bridge to be balanced, what is required? That zero potential difference should be between the terminal of this detector. So for that, what should be the case? E1 should be equal to E2 and E3 should be equal to E4. Okay. So this should be the case. Means magnitude, obviously. Magnitude should be what? It should be equal. Tell me if this is clear or not. Simply I have done what? I have applied KVL. I have applied KVL over here and KVL over here. Okay. That's it. Is it clear? Any doubt? Tell me. Okay.
Yes.
So, okay, fine. So now let us do what? Once again, let me take current over here. So let this be I1 and this be I2. Okay, I have decided that the AC current at a particular cycle is flowing in this direction. So if this is the case, so I1 will be equal to what? So I am at balance bridge, okay? at balance bridge condition. This will be the condition. So I1 will be equal to what? It will be equal to V divided by Z1 plus Z3. So this is in complex form. I haven't written in your in your polar form. Okay, this is in complex form. And I2 will be equal to what? I2 will be equal to V divided by Z2 plus Z4. Okay. Now simply take any one of the equation, either this one or this one. It's up to you, whichever you want to take, and equate it. So E3 will be equal to what? I am taking this one, okay? E3 is equal to E4. This implies this will be equal to Z3 into I1 is equal to Z4 into I2. So Z3 divided by Z1 plus Z3 into V is equal to Z4 divided by Z2 plus Z4 into V. V gets cancelled. Cross multiply. Z2 Z3 plus Z3 Z4 is equal to Z1 Z4 plus Z4 Z3. So what you can cancel? Z3 Z4. So what you get? The condition for balance bridge is what? Z2 into Z3 is equal to Z1 into Z4. Once again, we are getting the same condition that your product of the impedance of the opposite branches should be equal. Z1 into Z4 is equal to Z3 into Z2. You can see. Any doubt up to this point? Any doubt? Now, this is very, very important. Why did I then write all this form? To waste our time or what? No. See, you have to pay very good attention. See, these are basically the impedances. Impedances. Now, if I put the polar form in this expression, what it will be? Z2 into what was the condition? Z2, Z3. Okay. Is equal to Z1 into Z4. Now put the magnitude and phase form. So this will be magnitude of Z2 phase of phi2 into magnitude of Z3 into phase of phi3 is equal to magnitude of Z1 into phase of phi1, phase of Z1, magnitude of Z4 into phase of Z4. Okay. So now basically this condition should be satisfied. So I can break this into two parts. First part is magnitude condition. For an AC bridge to be balanced, there are two conditions. First is the magnitude condition. What does the magnitude condition states? That magnitude of Z2, Z3 should be equal to magnitude of Z1 into Z4. And second condition, for the bridge to be balanced, simultaneously these two conditions should hold. Another is your angle condition. What does the angle condition states? That phase of this two, or you can simply write it like, because you should be knowing in product phase basically add, so it's okay. I will write it like this, is equal to 1 plus 5. So for the bridge to be balanced, simultaneously these two conditions should be true, or else your bridge is not true. See, I will show you one question, one or two question, where your magnitude condition will be hold true, but angle condition will not be true. At that time, bridge will not be balanced. And that is one of the best question ever asked in GATE, because most of the student, they will give wrong answer. Why? Because in each and every coaching, they are actually told check using magnitude condition. Because 99% of the question where magnitude condition is satisfied, they are actually balanced bridge. But in that 1% only, we have questions where magnitude condition is satisfied, but angle condition is not satisfied. And at that point, we are going to say bridge is unbalanced. Okay? Tell me, is it clear? Is it clear? Any doubt? So note down whatever I said. Okay, so one more point. Now you might be asking, sir, when to check both the condition? See, so I will tell you one trick also. When AC bridge, if any one of the arm in the AC bridge have ideal resistance, inductance or capacitance, at that time you are going to write what? You are going to even check angle condition. Now what is this ideal RLC? So you should be knowing, see, basically inductor that we study, this is your ideal inductor. Practical inductor is something like this. There is always a very small value of resistance with it. Okay, so this is actually your practical inductor and this is your ideal inductor. So if in an AC bridge we have ideal resistance, inductance or capacitance, at that time you have to check angle condition. See, this is our ideal capacitor, but if you see the practical capacitor, so there is a very small value of R in your series. Even we ignore it. Even in your practical circuit, we ignore this thing. It is okay. But there is a very large value of resistance. Very high. It is in your mega ohm region. Okay. Mega ohm region, we have a resistance that is in parallel with the capacitance. So this is what? This is your practical capacitor. So most of the time in AC bridges, you are going to see that any one of the arm of your this AC bridge, there is connection of RL, RC. Okay. Whenever you have a single element capacitance or a single inductance, at that time you have to check both the condition. Tell me, is it clear? Any doubt? Please tell me. So make a note point that we need to check both magnitude and angle condition whenever any one of the arm of AC bridge contains only R, L or C. Make a note point. Noted? So now next thing we have to study is power factor. So what is power factor? What do you mean by power factor? Anyone?
It's that we can say phase difference between the resultant voltage and resultant current.
Very good. You can say basically power factor is what? It is the difference, phase difference between resultant voltage and resultant current. Phase difference or cos of phase difference. Phi. Hello, am I audible? What happened? My screen sharing, it's not showing. Hit the recording. Yeah, so I was telling what? That power factor is actually the cos of angle of phase difference between resultant voltage and current. Now, one thing we have seen even in your power factor is actually equal to R by Z in your series RLC circuit. Okay, series RLC circuit. So what I can do, I can multiply and divide with I square in the numerator and denominator. So what is this? I square R is your real power. And what is I square Z? I square Z is your total power, or which you say apparent power. So basically, your power factor is what? It is the ratio of real power by total power. So there is one more definition also of power factor. Tell me, any doubt in this? Any doubt? So power factor, one more thing we can know, that power factor, it lies between 0 and 1. Another characteristics. And power factor is basically what? Power factor is your dimensionless quantity. Okay. So power factor is what? It is your dimensionless quantity. Okay. Any doubt up to this point? Anyone? So just give me a second. Okay. Okay. So power factor, I just thought that I will let you know what is power factor. Okay, one more thing that we need to know is quality factor. Have I written somewhere? Quality factor we haven't written. So let me talk a little bit about quality factor. What is quality factor? So can anyone tell me what is quality factor?
Sir, energy storing capability for the energy storing elements.
Very good. So basically, quality factor is that of a practical inductor or a practical capacitor. So quality factor, like I told you, in a practical inductor, we have your resistance part, and in capacitor, we have a resistance in parallel. So don't tell me the definition. Can you guys tell me what is the significance or what does quality factor tell you with respect to these two diagrams? These two are, this is your practical inductor and this is your practical capacitor. Yes, tell me now.
It says that how dominant L and C are in this circuit.
Acha Nitish, I might have told you this in the class, na? I
Yes,
forgot.
sir. Yes.
So it's okay. So Nitish actually he has studied. So I from me only network. So I am asking the same question. So basically, Shishir and Sunny, do you know actually what is the practicality of this quality factor, or what does quality factor tell you? Do you know this, Shishir, Sunny?
No, sir, I haven't read it yet.
Okay. So basically, quality factor, as the name suggests, it tells you about the quality of your practical inductor or practical capacitor. See, when you are purchasing an inductor from market, it is something like this. Now, what will happen if the characteristics of resistance is more dominant than the inductance? Is this a good inductor? Means you have purchased an inductor, you didn't wanted a resistor, but you are getting that the resistive quality is more, sorry, the resistive part is more in that inductor. So this is actually a bad quality inductor. Similarly, in capacitor, what happens if your resistance part, it starts to decrease, means here you can see what, that this is in parallel. Resistance over here is approximately equal to infinite. So whenever a smaller value is in parallel with a higher value, you get an answer that is approximately equal to the smaller value. Like when your 10 ohm is parallel to 100 ohm, so if you solve this, so this will be 10 into 1000, sorry, 10 into 100 divided by 110. So this will be 1000 divided by 110. Approximately this will be equal to 10. 9 point something something, but it will be approximately equal to 10. But now what happens if this value starts to decrease? If you keep on decreasing this value, if suppose you do 10 parallel with 20, so now what you get, 10 into 20 divided by 30. So this is 20 by 3 or 6.66. Now you cannot say that this is approximately equal to 10. You cannot say so. So similarly, in your practical capacitor, if this R value starts to decrease, your quality of the capacitor is decreasing. So basically, the quality factor states us that in an inductor or a capacitor, how good is the quality of the inductance and the capacitance part respectively. Did we understand or not, Shishir and Sunny? Tell me yes or no.
Yes, sir.
Okay, fine. Chalo. Up for quality factor, the definition that we have studied in the book, let me write that for you. Okay, so quality factor, as textbook says, it is equal to 2 pi into what? Energy stored in one time period by LC, either by L or by C, divided by energy dissipated, or the average value of energy dissipated in one time period by your resistance. Okay, so this is what, this is your quality factor. So I always tell, whenever you are reading or studying something, please understand what is the significance or how it is actually applied in your real world. Okay, so you should be always knowing this thing. Okay, fine. So we even read about quality factor. Now there is one more thing that we should know. It is the dissipation factor. Now, can anyone tell me what is dissipation factor? What is dissipation factor? Dissipation factor is nothing but, you, if you understand the name, dissipation. What do we mean by dissipation? Dissipation means loss, is getting dissipated. So what is basically dissipated over here? Energy. Now out of this element, okay, L, R or C or R, which element is dissipating? You will say resistive part. So dissipation factor basically states us that in an inductor or a capacitor, how much is the energy dissipated by the resistance. Okay, so dissipation factor is actually inverse of quality factor. Quality factor states us how good is the quality of inductor or capacitor with respect to the inbuilt resistance, and dissipation factor basically is what? It is just the inverse of quality factor. It states us that basically how much energy is dissipated by this R part. Tell me, any doubt in this? Any doubt? Any doubt, anyone? Chalo, to fir let us go ahead. Okay, so now we have what? Sources and detector. Okay, sources and detector. Now basically Over here you can see that this is your source. Any doubt, Shishir?
No, sir.
So this is your source and this is your detector. So what are these sources and detector? That also we need to know. Okay, if we are studying, it's not asked in GATE, but still we need to know. So if we are measuring low frequency, okay, for low frequency measurement, we can use our normal power line that has 50 hertz. Okay, we can use this if we are measuring low frequency. For high frequency, we have electronic oscillators. Okay, we use electronic oscillator as your source. Okay, so these two are source. I talked about source. So if we have high frequency measurement, we use normal power line as our source. Usually in your labs, we use this only, low frequency measurement. Now, high frequency measurement, if we are doing, then we require electronic oscillators. Can anyone tell me what is one electronic oscillator? Example. Electronic. अरे इलेक्ट्रिकल वाले हो सब है ना. नाउ डोंट टेल सर वी डोंट नो. It's okay. Even I didn't know. Voltage controlled oscillator. You can generate. Even nowadays, this thing, this cathode ray oscilloscope, they also have this inbuilt feature of generating high frequency signals. So even you can use that. Okay. Have you seen voltage controlled oscillator, VCO? Don't tell, sir. We don't even recognize what is VCO. So it's okay. Anna. So that is why actually I will tell you one short thing. So that is why India, we Indians, okay, I will not tell it that a particular people, we Indians, we don't have a knack for your this thing research because we don't know exactly what are the things. Okay. So even I have done MTech from IIT. It's okay. But what is the significance? I have published 3 papers. Okay, one of the paper is useful. Remaining 2, it's not useful. It's theoretically useful. And why does it happen actually? Because directly from your BTech, I switched to MTech. So I didn't have any industrial exposure. I didn't know what is the industrial culture, what is the industrial problems that are faced in industry. So if you are working someplace at that particular place, you might get certain situation where there are problems. Okay, there are problems. Now, if you are an electronic engineer, there will be different problems in your domain. If you are an RF engineer, there will be some problem. But those problems you will get to know when you are on field. And when you are on field, you get to know about the problems faced by others also. And after that, when you go to MTech, at that time you can pursue a research on those problems. But when you directly jump from your BTech to MTech, what happens basically that you don't know anything what is the problem. Once again, you are going and searching for problems from your textbook. Okay, you are searching what other people have published in their research paper, what were the problems faced by them, and you are trying to remove those problems. So you are actually working on finding solution for someone's problem, not the problem that is actually faced on field. So this is the problem that is faced by engineers in India. Even after having such huge quantity of engineers, we don't know actually what is happening. So this is actually the sad part, जिसको विडंबना कहते हैं हिंदी में. Sad part, saddest part you can say of our education system, that we don't even recognize what are. I am not pinpointing you guys. Nobody, even I didn't know. Okay, I didn't know how to operate CRO जब IIT गया था तब भी. I didn't know how to operate CRO. what is x-axis, what is y-axis. I didn't know in CRO how to set those things, what is sweep. So it's okay. How many of you don't know? Tell me. Do we know the proper operation of CRO? Nitish, Shishir, Sunny?
No, sir, not properly, but I have used once or twice CRO.
Once or twice, it's like Avenger series, okay? You are turning all the knobs and seeing, oh yes, it's working.
Yes, sir.
Okay. Yeah, so I know. Okay, even I am from a private engineering college, so I know what all things happen. Okay. So this is actually the sad part. If you go to foreign countries, why are they very much progressive in research field? Because they don't even allow people directly who have actually done an engineering, and they don't allow people to directly jump into this thing. If you have internship, then it's okay. If you have like 1 year internship you have done at some place, it's okay. But if you are directly going from academics once again to academics, you don't have any knowledge. Why do people do research? To find out problems and then means finding solution for those problems. But if you don't know the problem itself, then how are you going to find solution? Like when I went for my MTech, I asked my professor, my guide, sir, what should I do? I don't know. I don't know in which field I have to do research. And he was like, बेवकूफ हो क्या तुम IIT क्यों आ गए? Okay. So I am 100% sure when he was also doing PhD, at that time he also didn't know what was happening. Okay. So these all things carry forward. So I feel very bad. So that is why people who ask me, sir, whether I should join job or should I directly go for MTech, I tell them, see, your gate score is valid for 3 years. It won't go anywhere. But if you are getting to work in a very good core sector job, work over there for 1 year minimum, try to understand what is going on and then go for your MTech, you will excel a lot in your field. Hello. इतना तो बोला, at least you guys can also keep this thing in mind. Okay.
Yes, sir.
Sunny, Nitish, have you guys seen CRO? Do you know the proper working of CRO? If I ask you simple, just measure time period of a signal, will you be able to do using a CRO? Okay, Sunny can do. Yes, he can do. So that is very good. So out of 3 people, only one can do. So 33%. Okay. At this particular time, 1/3. Okay, so it's okay. Chalo, koi baat. So I was telling about source and detector. Okay. So now detectors, I talked about sources. Now what about detector? So detector, there are various detectors that we can use. A simple detector is what? If you are measuring DC, you can use simply DC galvanometer. So this can be used only for zero frequency. Okay, zero frequency line. Now we have what? Primitive galvanometer, like vibration galvanometer. These are all extinct, like dinosaur. Okay, you might see in your college lab. Okay, vibration galvanometer. So it works in the range of like 0 hertz to 1 kilohertz. So these are all analog instruments. These are very costly. Okay, so vibration galvanometer. So it can measure in the range of 0 hertz to 1 kilohertz. Then we have tunable galvanometer. So this is like a big TV. Okay, this tunable galvanometer, it is like a small television that we had. Okay, like 10-20 years ago, that big television, CRT monitor television, it's of that size. Tunable galvanometer. So it can measure in the range, I think, if I am not wrong, just once check, I don't know, 500 hertz to 5 kilohertz. Okay, this is also extinct. Somewhere you might find. Okay, tunable galvanometer. Then next we have like telephonic galvanometer. This is used still. I don't remember the range for this one. Please find out yourself. Telephonic galvanometer, I think it's more than 10 kilohertz. Okay, more or less, I don't exactly remember. I don't remember. It's actually 10 kilohertz. I don't remember whether it is greater than 10 kilohertz or less than 10 kilohertz. 10 kilohertz I remember. Okay. And last is that is the most versatile detector. Okay. You can use it for any frequency. It is your CRO. CRO. You can even use it for low frequency, high frequency to the range of 10 megahertz. That is the most versatile detector available these days. It is what? Cathode ray oscilloscope. Okay, chalo. So next we have to see what? First thing in the AC bridge is measurement of inductance. So up till this time, are we enjoying the classes or not? Tell me yes or no. Boring तो नहीं लग रहा है
Yes,
ना?
no, sir, very much enjoying.
Okay. What about Sunny and Nitish? Not enjoying? Ah, it's boring, sir. बिल्कुल. Enjoying, chalo, enjoying. So let us enjoy then. Okay. So the first thing that we are going to measure is what? We are going to measure inductor. Now, in means not inductor, sorry, inductance we are going to measure that of an inductor. Okay. So inductance we can measure, basically we can measure using lot of bridges, but for our syllabus, we can measure it using 4 bridge. Okay, 4 bridge. Now the first that you might have even experimented on, it is your Maxwell bridge that is used in your college labs. Okay, you might have seen Maxwell bridge for the measurement of inductance, I guess in your fourth semester, fifth semester. I have studied this in your fifth semester electronic measurement lab. Okay, so Maxwell bridge. So Maxwell bridge, basically we measure the inductance of an inductor that has medium quality factor. So all the medium quality factor coil, we can measure the inductance. Medium quality factor means what? The coils that are available in your market. Okay, in your market, those are the coils. You can measure the inductance using Maxwell's bridge. Next, if you want to measure very high quality inductance, means inductance of an inductor, that you can measure using Hayes bridge. Okay, so it measures basically inductance of high quality factor coil. Okay, next is your Anderson bridge. So Anderson bridge, it basically measures low quality factor coil. Low quality factor coil means what? Where your resistive part is comparable to your inductive part, comparable to inductive part. So at that time we use Anderson bridge. And so where do we use Owen bridge? Can anyone tell me? Owen bridge. Now I remember there was this experiment of Owen bridge, but I just copied the result, okay, from my senior's book. Okay, so that lab manual we have now, so I copied it. I don't know what was the experiment also. So Owen's bridge is basically used for calculating magnetic permeability. Have we heard this term? Have we heard this term, magnetic permeability, denoted by mu r? Okay, mu r. So we are going to see this. Now at this moment, I am not defining what is magnetic permeability. Later on, when we study Owen bridge, at that time, I am going to tell what is magnetic permeability. So inductance in our syllabus, we have 4 type of bridges. First is Maxwell bridge. Maxwell bridge is used to measure quality factor of means inductance of a coil having medium quality factor. Hayes bridge is used to measure that of high quality factor coil, and Anderson is used for low quality factor. So let me even write. So medium means quality factor in between 10, high means quality factor greater than 10, and low means quality factor less than 1. Okay, so these are the values. Any doubt up to this point? Tell me yes or no. Any doubt? Okay. So now let us see the first bridge, which is your Maxwell bridge. Now, one thing I will tell you, it's okay if you are able to memorize this diagram, it's okay. If you are also not able to memorize the diagram, then also it's fine. Okay, it's okay. So look, this is your Maxwell's bridge. So in Maxwell's bridge, basically, this is your unknown coil. I am telling coil. Coil means basically resistance and inductance. Okay. The inductor that is available in the market, which has a small value of resistance also. So that is what? That is your coil. Okay. So I need to measure the value of this R1 and L1. So now see how do I basically do the calculations. Okay. So basically over here, let me write this as Z1, this as Z3, this as Z2, and this as Z4. So Z1 is equal to R R1 plus J omega L1. Please don't note. Later on, I will give you time to note. First, just see. Z2 is equal to what? R2. Z3 is equal to what? It is equal to R3. And Z4 is equal to parallel combination of R4 and C4. So I can write it like R4 into 1 by J omega C4 divided by R4 plus 1 by J omega C4, or you can simply write it as R4 divided by 1 plus J omega R4 C4. So this is what? This is your Z4. Now, for the bridge to be balanced, okay, so we are going to take the measurement of this. Just give me a second. So we are going to take the measurement of this resistance and inductance at balance condition. Okay, there might be a galvanometer, it might be a tunable galvanometer or a CRO, whatever it is. I am taking basically at null condition. Okay, so at bridge balance, we know what? Impedance, product of impedance of the opposite branches, it is equal. So Z1 into Z4 is equal to Z2 into Z3. Now here you can see this is actually practical inductor, and here we have a combination of resistance and capacitance. So directly I can use the magnitude condition. Okay, you can use the magnitude condition also, or simply if you don't want to use the magnitude condition, simply put all the values. Okay, put all the values. So you will be seeing R1 plus J omega L1 into Z4. So Z4 is this one. R4 1 plus J omega R4 C4 is equal to Z2 Z3. So that is R2 R3. See how to do the calculations. Please see over here. Don't note. Okay. Later on you can note. So this is equal to R1 into R4 plus J omega L1 R4 is equal to R2 into R3 plus J omega R2 R3 R4 C4. Tell me, up to this point, is it clear? Is everything clear? If it is clear, please note down up to this point.
Yes, sir.
So note down. Noted? Noted? Chalo. So now you can see what? That basically I got this equation. Now for this to be satisfied, what you have to get is this R1 into R4 means by equating the real and imaginary part, this should be equal. And second is what? Omega L1 R4. This is equal to what? Omega R2 R3 R4 C4. So you can cancel R4 R4 omega omega. So what you get? L1 is equal to R2 R3 C4, and from here you can get R1 is equal to R2 R3 by R4. So you can see already this is unknown. This R3 and R2, these are the fixed arm of your this Maxwell bridge. Now, how to basically bring this detector to null position? So for that, what can be the variable parameters with the help of which we are going to know the value of R1 and L1, or with the help of which we can bring this detector to null position? So by varying R4 and C4. Now, how did I actually determine this? Look at this expression. Look at this expression. So I have already calculated R1 and L1. These two were my unknown. So if you check over here, what you can see, here we have R2. I will use some different color. See, if I take R2 as my variable, so what might happen? If I change R2, L1 and R1, both of them are going to change simultaneously. It is going to affect both R1 and L1. Hence, your bridge might not converge. Converge means what? That your bridge might not go towards the null position. Okay? It might diverge. So look over here. Any other quantity R3. So even R3 is present. So I cannot even take that. So it is always necessary that you take uncommon parameters for setting the value. So you can see in these two values, C4 is uncommon. It is not present over here. Even over here, R4 is not present over here. So that is why I told for bringing this detector to null position, basically I vary R4 and C4. Okay, so with the help of R4 and C4, I bring this to null position, and the moment we have null position, we already know the value of R3 and R2. This is fixed. R4 and C4, by variation, we know what is the value because we have varied this R4 and C4. So we can see the value of R4 and C4. Hence, we can determine R1 and L1. Tell me, is it clear? Any doubt? Any doubt, anyone? So remember, R1 is actually function of R4 and L1 is actually function of C4. Okay, so we always select uncommon parameters as our variable. Write it down over here, one note point. Select uncommon parameters as variable. Okay, so this thing needs to be noted. Any doubt? Any doubt? Fine. So chalo. Next, what we have to see? Next, let us see quality factor. Any doubt, Shishir?
Yes, sir. मतलब sir, how will we vary R4 and C4? मतलब simultaneously will vary or will vary मतलब?
No. Okay, so that is a very good doubt you have asked. So how do we actually do? Okay, so look, So this is your galvanometer. Okay, this is your galvanometer. This is your zero. Suppose initially, okay, initially you have connected this. Now this R4 and C4, it might be on a particular value, okay, it might be 0 or it might be set to some random value, we don't know. And for that particular random value, let your galvanometer is detecting something like this. Okay, now what is our aim? Our aim is to find this R1 and L1. Okay, R1 and L1 by varying R4 and C4. So L1 is equal to what? It is equal to R2 R3 by R4, and C1 is equal to what? R2 R3, sorry, R1 is equal to this and L1 is equal to R2 R3 C4. Now what I can do over here, as these two are independent, okay, R2 and R3 is already fixed. R1 is inversely proportional to R4 and L1 is directly proportional to C4. So what I do, I start to vary C4 or R1. It's up to you. You can vary any one. Simultaneously, you cannot vary both. So I started by varying R1. So when I started varying R1, if suppose I increased R1, so what is happening? This needle is coming towards this side. Fine. That means it is converging. It is coming towards null position. But after certain value, you might see that if I increase beyond this value, suppose at this point, if I increase the value of R beyond this point, once again, this pointer is moving away. So at that particular point, I will fix this R1. Sorry, I will fix this R4. This R4 is now fixed. Because if I increase it more, again your deflection is starting to diverge. It is not converging. Now at this particular moment, I will start to either increase or decrease C4, which will cause the pointer to come towards this side. Now at a particular value of C4, either this will converge exactly to the null position or very, very near to the null position. So now did you understand, Shishir, how basically we set?
Yes, sir.
चलो आगे बढ़ते हैं. So what I was telling, quality factor. So quality factor we have to calculate. Quality factor of what? Quality factor of this unknown coil. So already in your network class, you know that quality factor of this is what? Omega L1 by R1. Do we know this or not? Shishir and Sunny? Shishir?
I remember the formula, sir, but we haven't read it
Haven't
in
you
our
attended
later
the
class.
classes?
Actually, sir, it was the start of the COVID season, and we were given
No. I
coil.
am asking start of COVID season reason nahi. I am asking our IGC class taken by
No, sir.
Prashant sir.
No, sir. It's this topic is not started yet.
So where are you guys at this point?
I think the transient we have started for the DC.
Transient for DC? अरे transient DC के लिए ही होता है.
Behavior of yes, sir. Starting of the transients we have started actually.
So what all things you have completed? It's like, so what all things are completed, Shishir?
So I think theorems we have completed, mutual inductance we have completed, capacitance. That's all I
Okay,
think.
चलो कोई बात नहीं. It's okay. So you are going to study. Okay, you
Yes,
are
sir.
going to study basically that in your RL circuit, quality factor will come out to be omega L1 by R. So I am not going to discuss that because then I have to draw the phasor diagram and all those things. So I will skip that part. You can later on see in the class. So quality factor of a coil, it is given by omega L1 by R1 in this particular case. So L1 value we already have. And R1 value, this also we have. Okay, R2, R3, yes. So now we can cancel this. So this comes out to be omega R1C4. So this is the quality factor. Wait a minute. Sorry, this is R4, na? So you can see quality factor of the coil, it is equal to omega R4C4. And this is very interesting result. Why? Because if you see what is the quality factor of your capacitor, what is it? What is the quality factor? What is the quality factor?
By omega RC.
Huh?
1 by omega RC.
1 by omega RC. Now you can see basically that the quality factor of this particular unknown coil is inversely proportional to the quality factor of this variable capacitor and resistance. So once this question, I think last year only this question was asked in your this thing, multiple select type, or I don't exactly remember. There were few options given, and it was asked that in your Maxwell's bridge, the quality factor of the unknown coil depends on what? So you should have said that the quality factor, it depends on your basically inversely it depends on the quality factor of the variable resistance and the capacitance connected in the parallel. Tell me, is it clear? So this quality factor is under balance condition, remember. Under balance condition. Is it clear?
Yes, sir.
Okay, fine. So this is what? This is your quality factor. Okay. So one thing, this we got quality factor. Now one thing I want to share, that basically what we saw, that for getting this L1 it was R2, R3, C4. So variable capacitance, because we are varying C4. Variable capacitance is very, very expensive. So write one point, Maxwell bridge setup is expensive. Maxwell bridge setup is expensive. Maxwell bridge setup is expensive due to the fact that variable capacitors are expensive. Okay. Next, very important point, Maxwell bridge is independent of operating frequency. You can see, I can get the value of R1 and L1 at any operating frequency. It can be 50 hertz, it can be, means not hertz, this is in radian actually. Okay, so 50 hertz, 100 hertz, any frequency, I can get the value of R1 and L1. Now that doesn't mean you are taking 0 hertz. ऐसे कैसे मतलब, this is DC value. So you cannot make an AC bridge operate in a DC condition. Okay, so you cannot do that. So you can make it work in any of the frequency because Maxwell bridge is independent of frequency. Next point, Maxwell bridge is the simplest modification of Wheatstone bridge. It is the simplest modification of Wheatstone bridge. Okay. Is it clear? Any doubt? Is it clear? Now, one thing I want to ask you. Sir, you told us this point. Maxwell bridge can be measured for medium quality factor. Why did you say so? Have you read it in the textbook? That is why you are saying us. There should be some logical explanation for what you are saying. You guys didn't ask. So what should I do? I shouldn't tell then, or should I tell you guys? क्या बोलूं बताओ, बोलना है कि नहीं बोलना है? I wrote all this thing that Maxwell can be used for only medium quality factor. Do you want to know the reason why? Oh, chalo, I will skip. It's okay. If you guys don't want to know, it's okay. Then why should I say? Okay, so you want to know. Chalo, as you are requesting, you guys, so I will tell. Okay. Now look very carefully. There are 2 points that I want to say. अरे कहाँ लिख दिया point? Where is that point? Okay, so I didn't write. So while I was dictating over here, I told that Maxwell bridge is a costly setup. Why? Due to this factor, variable capacitance. Fine. Now look at this quality factor. Quality factor. Quality factor is equal to omega R4C4. Basically, this is quality factor of what? This is quality factor of coil. Okay, this is quality factor of the coil, which I have equated it to this. And this is under balance condition. Please don't note. Please don't note. Understand. Basically, we are getting this null condition. We are getting this null condition by varying this C4 and R4. So basically, what is this? We are varying the quality factor of the coil with respect to the quality factor of the resistance and capacitance. Now, if I have a high quality factor coil, what will happen? This bridge will never converge. Why this bridge will never converge? Because at that time, I will be requiring a variable capacitance that has high value. Why? Because high quality factor coil, if I have over here, suppose if I have a quality factor that is greater than 10. So to balance the bridge, I will require a value of capacitance that is also very, very high. So a very, very high value of variable capacitance, that module, it will be very, very costly. So that is why we never use high quality factor coil in the measurement of your inductance in Maxwell bridge. Did we understand what I tried to say? समझे कि नहीं?
Yes,
Everybody
sir.
tell me. Shishir, any doubt?
No, sir.
Sunny, did you understand? Or once again, should I explain? What did I say? Basically, if you have a high quality factor coil means inductor, unknown parameter, R1 and N1. So if you have a very high quality factor coil, so to actually bring the bridge to null condition, I will be requiring a very high quality capacitance or a high value of capacitance. And a high value of capacitance can only be achieved if I have a very, very costly variable capacitance. So that is why actually we avoid, because here your balance is basically dependent on the value of R4 and C4, as these two are variable. So for a high quality factor coil, I will be requiring a higher value of capacitance to balance the bridge. Is it clear? So this is the reason why we don't use high quality factor coil for measurement in your Maxwell's bridge. Now next is what? Hayes bridge. Hayes bridge, I have told you, you can see it is used for the measurement of high quality factor coil. Okay, measurement of inductance of high quality factor coil. So similarly, once again, this R1 and L1, it is unknown. I don't know. At this time, we also don't know by varying which factor I will be getting the bridge balance. Later on, we are going to see. So let us start the analysis over here. Z1, now I am writing directly. This is Z1, this is Z3, this is Z2, this is Z4. Okay. So Z1 is equal to what? R1 plus J omega L1. This is the last bridge for the day. Okay. After this, we are going to stop. So Z2 will be equal to what? This will be equal to R2. Z3 is equal to what? It is equal to R3. And Z4 is equal to what? It will be R4 minus J by omega C4. Okay, so this is what we have. Now for bridge to be at balance condition. Okay, at balance condition, what we know? Z1, Z4 into R4 minus J by omega C4 should be equal to R2, R3. Okay, it should be equal to R2, R3. Now, if I open this, so let me do it directly. R1, R4, and from here, okay, so this will be plus omega L1 divided by omega C4. I am separating the real part and imaginary part, plus J omega L1 R4 minus R1 by omega L1. Please check if this is correct or not. Okay, so sorry, this is C4, na? Omega C4, okay, is equal to R2, R3. Tell me, up to this point, is it clear? Simply, I have done it in a single step. I hope you guys had your lunch. Lunch हो गया है सबका कि नहीं हुआ है? Did you guys have your lunch? Yes or no? No? अच्छा. So that is why you guys are now like, sir, please छोड़ दो आप, है ना? It's Sunday. Sunday, please leave us. So it's okay. I can understand. Okay. चलो कोई बात नहीं. Within 5-10 minutes, I will leave you guys. Okay. Okay. Fine. So now for this bridge to be balanced, what we can see, first thing is R1 into R4 plus omega omega will cancel. This should be equal to R2 R3, equation 1, and this value should be equal to 0. Omega L1 R4 minus R1 by omega C4 should be equal to 0. Equation 2. Okay, this two equation we have. So let us try to solve this. So this is equal to what? If I bring this over here, omega square L1 R4 C4 is equal to R1. Okay, this we have. Or if I solve it over here, R1 is equal to omega square L1 R4 C4. Okay, now what we can do? This let this be equation 3. So it's okay. Let us plug this equation in this equation. What do we get? Let us see. So from 1 and 3. Okay. So this will be equal to omega square L1 R4 square. Please pay attention. I might make mistake. So R4 square C4 plus L1 by C4 is equal to R2 R3. Okay, so let us take L1 common. So this is, can we take L1 by, let us take L1 by C4 common. Okay, L1 by C4 common. So this will be omega square R4 square C4 square plus 1 is equal to R2 R3. Now let me shift this C4 over this side. What do I get? L1 is equal to R2 R3 C4 divided by 1 plus omega R4 C4 whole square. See if this is clear or not. Up to this point, is it clear? Quickly see. If it is clear, please note it down. Note it down quickly. Noted, everyone? Now see very carefully. I have a value of L1 that is independent of R1, and I have a value of R1 which is independent of L1. Now, why did I do so? Why did I make them independent of each other? Because both of them are unknown. Okay, both of them are unknown. So that is why I made them independent of one another. So this is the equation of R1. This is the equation of L1. Fine. So you can even do, means, sorry, this is not independent. Means if you have to make it independent, simply just multiply L1 over here, you will get it independent. R2 R3 C4 divided by 1 plus omega R4 C4 whole square into R4 C4. Okay, now it is independent. Okay, fine. So let this be equation 5. So now tell me, which parameters are you going to select for varying? Which parameters are you going to select? Which parameter? Okay, even if you are not able to decide, one thing let me ask you. Like your Maxwell bridge, it was independent of operating frequency. I have stressed this point. Okay, you can see over here that basically it is independent of frequency. But your Hayes bridge, it is not independent of frequency. So what will happen? What will happen due to this? If suppose this is my detector, if this is your detector, somehow by doing some manipulation, at the moment I haven't talked, by varying which all parameters, somehow what happens, you balance the bridge for a particular value, your bridge is balanced. What happens, because your Hayes bridge is dependent on frequency, continuously this will oscillate between a mean value. It might oscillate between this value at the frequency that is that of the source. Okay, it will oscillate basically at the frequency, whichever frequency I have applied over here. So it will keep on oscillating in between these two positions at the frequency of the applied source. So what might happen? This might cause consumption of energy. First point is consumption of unnecessary. See, I have even written double C. Okay, even I am hungry. So that is why I asked if you guys had your lunch or not. Unnecessary energy consumption. Okay. Second point, it might even destroy your detector in long run. Why? Because continuously, if you have applied a 50 hertz input, it is oscillating at the frequency of 50 hertz. So that is quite fast. Okay, quite fast. So it might destroy what? It might destroy your galvanometer, and your galvanometer is quite costly instrument. Okay, fine. Up to this point, did you understand? Did you understand? Tell me. I told you why this will be oscillating, because you can see here your R1 and L1, it is dependent on frequency. That is why frequency is continuously changing. Frequency will change continuously. That is why your null point will also deflect continuously. Now, which all parameters do we need to take over here? So in Hayes bridge, once again remember that this R4 and C4, these two are variable. Okay, these two are variable over here. Now, how do we basically select R4 and C4? You can see that R4 and C4 is present over here, whereas R4 and C4 is present over here also. Okay, but your R4 is more dominant in this place. Why? Because you can see R4 is present in the numerator, whereas this over here, it is present just in the denominator, that to a square. Okay, that to a square. So what we will do, first we are going to set R4. Why R4? Because R4 will play a very insignificant role over here. So first we are going to set R4 so that this thing becomes set. Once R4 is set, then we set C4, because C4 plays a very significant amount of role in both the places. So like this, first set R4, second set C4 for your balance condition. Tell me, is it clear? Is it clear? Fine. Now, I told you that Hayes bridge is usually used for high quality factor coil. I told you this thing in the first slide only. You can see over here this point and this point. Now I will be clubbing these two. Okay. Why actually in Hayes bridge we require or we usually measure high quality factor coil? Now I am going to show. So let us try to calculate the quality factor. Quality factor will be equal to, once again, omega L1 by R1. So omega, what is the value of L1? R2, R3, C4. R2, R3, C4 divided by 1 plus omega R4, C4 whole square divided by what is R1? It's very big. Omega square R2 R3 C4 divided by 1 plus omega R4 C4 whole square into R4 C4. R4 C4. Fine. So now you can see this denominator is cancelled. 1 omega cancel. R2 R3 C4 is also cancelled. Fine. So what we are left with? We are left with 1 by omega R4 C4. We are left with this. Is it clear? Tell me. Is it clear? Tell me. Up to this point, is everything clear? Now a very important concept we are going to see. Quality factor is equal to 1 by omega R4 C4. Now, what is the necessity of having high quality factor? You are going to see. If suppose I am measuring very high quality factor coil, very high quality factor coil I am measuring, Q is greater than 10. Okay. If Q is greater than 10, then 1 by omega R4 C4, this is greater than 10. Is it clear or not? This quality factor is that of coil. Coil means R and L. It is dependent on this. So what happens if your quality factor is greater than 10? So now omega R4 C4, it must be less than 0.1. Okay. Or you can tell omega R4 C4 is very, very less than 1. Can I tell it like this or not? Please tell me yes or no. Can I write it like this? Fine. Now, if this is the case, if I add or if I square both sides, omega R4 C4 square, it will be more less than 1. If I have 0.1, this is very, very less than 1. If I square both sides, so this will be 0.01, which is far more lesser than 1. So that is what I have written. Okay, that is what I have written. So now you can see I got this expression. So that means what I can write now, in the next page I am writing 1 plus omega square r4, sorry, 1 plus omega rc whole square. This is approximately equal to 1 because this value I have already derived it. It is very, very less than 1. So approximately this value will be equal to 1. Do you agree to this or not? Please tell me yes or no. Do we agree to this or not? Okay. As you are agreeing to this, now let us come back to this equation 5th and equation 4th. So what do you get now? L1 is equal to R2, R3, C4 because this value is approximately equal to 1. And if you write it over here, R1 is equal to what? R1 is equal to omega square R2, R3, R4, C4. Tell me. C4 square, sorry. C4 square. So now you can see that is why actually we use high quality factor coil. Now what is happening, you see. Now these two values are independent of frequency. Means this one is independent of frequency. Okay, this one is independent of frequency and over here we have frequency value. Now if I keep the frequency value even constant, or even if it's okay, let me remove it. So now you can see that even previously both of them were dependent on frequency, but at this time one of them is independent of frequency. When this happens, if previously this was fluctuating between these 2 points, now what will happen? It will fluctuate. Even now it will fluctuate, but the fluctuation will be very, very negligible compared to the last case. Tell me, is it clear? Is it clear? Any doubt? So this is why basically we use very high quality factor coil in your Hayes bridge to reduce this, what you can say, oscillation. Tell me, is it clear? Any doubt? So with this, we will be ending